All right. Previously what we've spoken of is applying Ampere's law to a wire that is carrying a current. And what emanates from that wire carrying a current is going to be a magnetic field. And we were able to use Ampere's law to calculate the magnitude of that magnetic field emitting from that charge carrying wire. So what we have here is we're going to assume that this will be an infinite sheet of charge. I've only drawn 4 wires here, but we'll assume that we have an infinite sheet of wires or charge. All right. Each one of these will represent a wire, and this will be, the black dots indicate that the current is coming out of the board, towards the camera, towards your eye. And what I've done here is I've actually drawn a green box, or I drew a box, a rectangle, around this infinite sheet of charge. And what we're going to do is we're going to try to determine the magnetic field from this infinite sheet of charge. That's the goal. So let me repeat that again. Our goal is to determine the magnetic field from an infinite sheet of charge. All right. So we're going to break down this box just a little bit. And so let's look at the vertical wall. So this is going to represent the vertical wall that is going to have length L. The overall sum of each one of from this point to that point, likewise this point to that point, is going to have a length of L. And our magnetic field is going to protrude out as such. Now the angle between the magnetic field and the length, phi, is going to be 90 degrees. 90 degrees. If we go now into our Ampere's law, Bi delta L, so this is going to be the magnetic field at some tiny segment along this length. So we have a large collection of delta L's along here. And then this becomes cosine phi. If our phi is equal to 90 degrees, then we can plug that in to our equation here of 90 degrees. Now the cosine of 90 degrees is 0. So this entire term becomes 0. So the magnetic field at the vertical walls is going to be 0. It's going to be 0. Now let's look at the parallel, the horizontal field line, or the horizontal sides of our box. So if we look at the top and bottom, so the top and bottom, our L, the length, is going to be parallel to our B field. It's going to be parallel to our B field. All right. So we apply this into Ampere's law, Bi delta L cosine. Now since it's parallel, our phi is equal to 0. So this becomes 0. This entire term here goes to 1. The cosine of 0 is going to be 1. Now this then becomes equal to B, the sum of each individual of the magnetic field. And if we sum up all the little delta L's we have along there, this becomes L. So if we sum up all the tiny incremental small magnetic fields for every delta L, we're going to get the total magnetic field for the entire length of this box, and L is going to represent the length of the box. Now we're going to have a BL for the top, and we're going to have a BL for the bottom. All right. Therefore, this whole equation here is equal to BL for the top plus BL for the bottom. All right. And this becomes equal to 2BL. Becomes equal to 2BL. Now, if we go back to Ampere's law, this is going to be equal to mu naught, which is the permeability of free space, times the current. But this would be if we happen to have one wire or one charge carrier. And so we have to multiply it by n, where n is equal to the number of wires. N is going to be equal to the number of wires. So let's solve this now. So what we have is, I'm going to erase this up here so we have a little bit more room to write. All right. So we have, so we're going to take 2 BL is equal to mu naught. I don't know why we're putting that into a parentheses. I don't know what I was thinking. This is going to be I, N, and we're going to solve this for B. So our B becomes equal to mu naught. This becomes I, N, all upon 2L is what we get here. All right, so that's how we solve for B. But let's look at now N upon L. And what N upon L is this is going to be the number, oops, I better put an equal sign there. This is going to be equal to